Hello, everyone. I know that it will be a little bit of noisy here on my end since actually I am here in Starbucks, Lacson, since we don't have any current in our place, so that's why I have to find any other option for me to record a video in terms of our classes, and so that you can definitely answer in terms of our quizzes or whatever. So right now we'll begin to deal with the threaded tree. I'll begin to discuss that here in this video. What is this all about? So for this threaded tree, that is actually, let me just go ahead and check. This is a type of binary tree where null of pointers actually left or right children are replaced by threads, and these threads point directly to the in order predecessor for left pointers or in order successor for right pointers. So I'll begin to illustrate that in a while on how to work on that, since there will be like a method on how to work on this specifically. So there will be types of trees as well for this I mean, there will be some types of threaded binary tree as well that we'll begin to illustrate in a while. There will be three types commonly that we will illustrate in the calculation. So in a normal binary tree, the null pointers are left empty. However, in a threaded binary tree, these null pointers are converted into threads, pointing to either the in order predecessor or in order successor. And these threads provide a more direct way to traverse day three. So we'll begin to illustrate that and how will you be going to work on with this. So there will be a types of threaded binary tree which will includes the single binary tree, a single threaded binary tree. Only the right null pointers are replaced by threads that point to the in order successor only of the current node. The left child pointers remain null or regular without any threads. So we'll be going to see that later on. Okay. So in a double binary a threaded binary tree, both the left and right null pointers, I'm so sorry, are threaded. So the left null pointers to the in order predecessor, and the right null pointers point to the in order successor also. So here then, each node in a threaded binary tree consists of the data, left and right child pointers, and the thread flags. So we'll begin to illustrate that so that we'll begin to understand on how to work on with this. So afterwards, when we say data, um that is the data field, host value, or element stored in the node. This can be any data type, such as integer, string, or object, depending on the use cases. And for the left and right child pointers, these pointers are used to navigate between nodes. In a threaded binary tree, a left pointer points to the in order predecessor and the node that comes before the current node in an in order traversal. We'll begin to see that actually on how to work on with this specifically. Then afterwards, there will be left and right child pointers. Right pointer as well points to the in order successor, the node that comes after the current node in an in order traversal. We'll begin to work on with that as well. So if the pointers do not lead to actual child node, they act as pointing to the predecessor or successor, eliminating the need for recursion as or a stack. So we'll begin to see that here. The thread flags is actually used to differentiate between regular child pointers and threaded pointers. So we will begin to mark as zero indicates that the pointer is actually a child to parent pointer, meaning it points to an actual child nodes. That is for the indication for the thread flags as well. We'll begin to see that in how we can definitely and identify those cases. And The one as well indicates that the pointer is a parent to child thread, meaning it points to either the in order predecessor left pointer or in order successor right pointer. And then here, the in order traversal using threads in a threaded binary tree in order traversal is simplified by utilizing threads for quick access to nodes. And so we actually start at the leftmost node, begin traversal from the leftmost node, which is the first node in your in order sequence. After that, for the in order traversal, by the way, the binary tree, we follow these structures like we traverse the left subtree first and we visit the root node, and then we traverse the right subtree afterwards. So how to work on that? For the single-threaded binary tree insertion operation, this will be the steps that we have to follow. We perform an in-order traversal. We start by performing an in-order traversal of the tree to determine the current location for the new node. And this traversal will give you the sequence of nodes, helping you find where the new node should be inserted. So we'll begin to see that we have to perform the in-order traversal in order for us to check the in-order successor and order predecessor afterwards. So here then, after you perform the traversal, um, this is actually identify the in order successor and connect with arrow. So find the in order successor of the new node, where the new node will be inserted. So we have to connect the right thread pointer of the current node to the new node successor. So I'll begin to illustrate that after later on in the example so that it will be um, clear for everyone. And then the third step will be defining the thread flags. It could be 0 or 1 respectively. As what I have mentioned, if it is parent to child and as child to parent also. And we assign the thread flags to differentiate between regular child pointers and thread. Set 0 for child pointers and 1 for thread pointers linking to the in order successor. And then here we have to create a dummy node and connect the dummy node successor to itself for the right position. So for creating a dummy node to handle the edge case of the last node in the in order sequence, set its right pointer to point back to itself with a thread flag of 1 also. And here that is the insertion of the binary a threaded binary tree for the single only. But for the deletion, we have to perform the in order traversal. This will be the step to find the node that you will be going to check that one. In order traversal, that is actually the bread search first, no, bread first search, traversal. I mean, no, in order traversal is actually a depth first search type. Start by performing an in order traversal of the tree to locate the node you want to delete. And this traversal will give you the correct sequence of nodes in the tree. And you can identify the position of the node to be deleted based on its value. So afterwards, you have to identify the in order successor and predecessor. After locating the node to be deleted, identify the in order successor and in order predecessor. The in order successor is the node that comes immediately after the node in the in order sequence, and the in order predecessor is the node that comes immediately before. And then we handle the deletion on the number of children. It depends on the case. Case one with leaf node, simply remove the node from the tree. If the node has the right thread pointer, the parent's right thread needs to be updated to point to the node successor. So we'll begin to illustrate that how we can work on with this structure. And then we handle the deletion based on the number of children. So one child, either left or right, replace the node with its only child. If the node has a right child, make sure the child's thread points to the correct in order successor. So it will be better that you will be going to identify the in order traversal once again, and then so that you can identify the in order successor and in order predecessor respectively, and we'll do that also. So the third step, handle the deletion based on the number of children. For two children, replace the node with its in-order successor and in-order predecessor. We adjust the thread so that the parent's right thread points to the new in-order successor. For in-order predecessor, by the way, for the deletion, if in-order predecessor, that is actually the largest number in your left subtree, and the in-order successor is the smallest number into the right subtree. That's how it works. And afterwards, the step where you have to revisit the in-order traversal after the node is deleted. Revisit the in-order traversal of the tree, and then to ensure that the tree's threaded structure is still intact. This traversal will help confirm that all nodes are correctly linked using the threads, especially the right thread pointer of the parent node. And then at this point, you can verify that the in order successor links are correctly pointing to the next node in the sequence. So after you perform such deletion, you have to perform in order traversal again in order for you to place that in a correct in order for you to simply correct I mean identify what will be the in order successor or in order predecessor, or what will be the thread pointer, where does that connect respectively. Then afterwards, the step five, adjust the thread pointers. Once you've confirmed the trees threading after the in order traversal, adjust the thread pointers as needed. If the deleted node had a right thread pointing to the in order successor, update the parent's right thread to pointing to the in order successor. Update the parent's right thread to point to the new in order successor, ensuring that all pointers are correctly threaded to maintain the efficient traversal of the tree. And afterwards, handle edge cases like the dummy node or last node. If the deleted node was the dummy node or the last node in the tree, handle the edge case by ensuring the right thread of the root or last node points back to itself. This ensures that no broken links or null pointers remain in the tree. So that's how you will work on with a single threaded binary tree. So only the rightmost in order successor that you will be going to work on with. But let's actually deal with a double threaded binary tree also. So for the double threaded binary tree insertion, we perform in order traversal first of the tree to find the correct position for the new node. This will give you the in order sequence, helping you identify where the new node should be inserted. So identify the in order successor and predecessor and connect with arrows. So we have to find the both the in order predecessor and in order successor of the new node, where the new node will be inserted. You have to connect the left thread pointer of the new node to the predecessor and the right thread pointer to the successor. So we'll begin to illustrate everything in a while in a different video also. Now, define the thread flags as zero for child, one for thread. Assign the thread flags to indicate whether the pointers are regular child pointers or thread. Use zero for child pointers, one for thread pointers, pointing to the in order predecessor or successor. And then create a dummy node and connect dummy successor to itself with the right. Um, Create a dummy node at the end of the tree to avoid null pointers. Set its right pointer to point back to itself with a thread of flag one. Then afterwards, perform in order traversal to find for the deletion. We have to perform the in order traversal to find a node. Start by performing an in order traversal of the tree to locate the node that needs to be deleted. In a double threaded binary tree, traversal will be done using both left and right threads, helping you find the correct node and its in order predecessor and in order successor. So once you've identified the node, in order identify the in-order successor and order predecessor. Once the node to be deleted is found, it identified the in-order successor and the in-order predecessor. These nodes are crucial for updating the threaded pointers after deletion. So the in-order pointers successor is the node that follows the current node and in the order sequence. And the in-order predecessor, it is a node that comes before that. And the next step, You have to handle the deletion based on the number of children. Case one, no children, simply the leaf node, simply remove the node and adjust the left and right thread pointers of its parent. The parent's left thread should point to the predecessor and the right thread should point to the successor. So it is really simple, but of course it will be better. You will be going to still work on with it in order to traversal afterwards. So handle the deletion based on the number of children with the case two, one child either left or right. So replace the node with its child. If the node has a right child, update the right thread to point to the successor. And if it has a left child, update the left thread to point to the predecessor. So afterwards, the two children replace the node with its in order successor, update both the left um and right threads of the successor parent and the predecessor parents point to the successor, ensuring that tree's threading is intact. And also, it is really in case two actually, case three actually, class, it depends if we'll begin to use in order successor, in order predecessor, but we will begin to illustrate that still. And for after performing the deletion, revisit the in-order traversal, perform a revised in-order traversal the tree to ensure to check if all the threads are correctly updated. In double-threaded binary tree, both the left and right threads must be checked and updated to ensure they point to the correct predecessor and successor. And for the step five, adjust the thread pointers. Once the in-order traversal has been completed, you need to adjust the thread pointers. If the deleted node was leaf node, or excuse me, or had only one child, make sure the threads of its third node are updated to reflect the correct in order predecessor and the successor. If the node had two children, the right thread of the predecessor should point to the successor and vice versa. Now, the step six for this, handle edge cases like the dummy node or last node. If the deleted node was the dummy node or the last node in the tree, in the case of a tree, using a dummy node to handle empty stats, handle the special case by ensuring that the right thread of the root node or the last points back to itself. This prevents broken links and ensures the tree remains consistent. We'll see that as well. Now, the advantage of this threaded binary tree, faster traversal. Threaded binary trees allows for faster tree traversal because they eliminate the need for recursion or stack by using threads to direct connect to their in order successor and predecessor. In the case of double threaded trees, traversal can be done in a more efficient manner. And then afterwards, memory efficiency can be more memory efficient than traditional binary trees since they do not require extra data structures like stacks or recursive calls to perform tree traversal. They save memory space. And it is also simplifies traversal algorithms with threaded by pointers. The need for complex algorithms is reduced. In threaded binary trees, nodes can be accessed directly via their threads, leading to simpler and more intuitive algorithms. And then no recursion needed. That means to say in threaded binary tree, traversals like in order, pre-order, and post-order can be achieved without the use of recursive calls, which is usually um especially is useful for systems with limited stack space. So of course, class, here then we will begin to focus with in order predecessor because of course if you will deal with pre-order predecessor I mean in order traversal only. If you'll begin to deal with pre-order and post-order here, it will be a big it will be complicated for you to manage. So we will work on with in order accordingly. Okay. So the limitations of this complexity in insertion and deletion operations in threaded binary trees can be more complex than in binary trees can be standard binary trees. When adding or removing nodes, the threads need to be updated and the in order successor need to be updated and in order successor and predecessor pointer must be correctly maintained, actually leads um which actually leads to overhead to these operations. And then afterwards, increased storage for thread flags. Each node in a threaded binary tree requires extra space for thread flags to distinguish between regular child pointers and thread pointers. And this increases the memory requirements for each node compared to traditional binary tree. So of course, the storage will really increase this, because there will be linking for the threads as well, because it must be threaded or connected to each other. And then limited to specific traversal. Thread binaries are primarily optimized for in-order traversal, while they can be adapted for other traversal like per order and post order. This requires more complex modification, and the performance benefit is not as clear. So of course, better to really work on in terms of in-order traversal alone. Now, not suitable for all use cases. Threaded binary trees may not be the best choice in situations where frequent modification, insertion, deletion are needed. So as managing threads with each update can be cumbersome. So additionally, it will be complicated because, for applications that do not require efficient tree traversal, the overhead of maintaining threads might overweigh the benefits. And then afterwards, database management systems. We can the applications of threaded binary trees, database, the BMS are useful in databases for indexing and efficient data retrieval. They can store our order data and support fast in order traversal, making operations like range queries and sorted data retrieval more efficient without requiring recursion or additional memory. And then afterwards, another application will be in file system. That means to say that we can use this to represent hierarchical structures, such as directories and subdirectories. And this can quickly access files or directories, improving performance for operations like file search and directory listing without using additional data structure. So another will be the expression tree. Threaded binary tree can be used to represent expression trees for mathematical expression. In such trees, each node corresponds to an operator or operand, and threaded pointers can help traverse the tree efficiently to evaluate the expression. So, and there will be memory constraint systems in systems with limited memory resources, such as the embedded system. Threaded binary trees are beneficial because they reduce the memory overhead required for tree traversal. Since they don't need extra stock space for recursive calls, they are an excellent choice for memory constraints environment. So here then for navigation system, threaded binary trees can be used in navigation system or games where fast traversal or of state trees or decision trees is required. For instance, in AI decision-making algorithms, threaded binary trees can help efficiently traverse different decision paths and quickly find the best course of action. Next will be compiler design for the syntax trees. So in compiler design or syntax trees, which represents the grammatical structures of programming languages, can benefit from third binary trees. Efficient traversal of syntax trees is essential for the task like parsing and optimization, and threaded binary trees can speed up this process by simplifying node traversal. So this is really one of the um, important thing that needs to be remembered by those computer science students. And then networking application. Threaded binary trees can be used in networking application for tasks such as routing, algorithms, or representing a network topology. Then fast in order traversal can be used to find optimal path or traverse network configuration in a more efficient manner. So here then, in order traversal, the time complexity will deal with the time complexity of threaded binary trees. For this, in order traversal, it will become linear time where n is the number of nodes in the tree. This is because every node in the tree is visited exactly once, and there is no need for recursion or a stack, making the traversal efficient. And then for the in-order traversal, we actually visited each one of the nodes. That's why. And pre-order and post-order traversal, In thread binary trees, while in order traversal is most efficient, pre-order and post-order traversal can be implemented using threads as well, but they may require more adjustment, and the traversal is still linear time. And then for insertion, time complexity of insertion will be O of H, that is still linear, where H is the height of the tree. This is because, like in regular binary trees, you must find the correct position for the new node, which takes time proportional to the height of the tree. So this is not linear actually. This is based on the height. It could be related to the logarithmic time. Now, deletion will be time complexity of deletion is also O of H, where H is the height of the tree. This is due to the need to find the node to be deleted and adjust the threading of its predecessor and successor pointers. And afterwards, the space complexity memory usage per node. Each node in a threaded binary tree typically contains data, left and right child pointers, and thread flags. So this space complexity per node is exactly constant time, as each node requires a constant amount of space regardless of the size of the tree. Now, overall space complexity will be linear time because the entire thread binary tree, where n is the number of nodes in the tree. This is because each node requires a constant allocation of spaces, including data, child pointers, and thread flags. And for the auxiliary space, there is no additional auxiliary space needed for traversal, as threaded binary trees use threads to directly link nodes, eliminating the need for recursion or stacks. Therefore, the auxiliary space is constant time. Okay, so that's the end of our discussion for the threaded binary tree, and I'll be going to illustrate that in another video on how to do the insertion and deletion respectively for the single and double threaded binary tree. Thank you so much and goodbye.